Hello and welcome to the fifth and final office hours for Alien Worlds during summer of 2015. So Aurora and I are here, and we'll spend the next hour answering your questions. So we have a bunch of questions already on the discussion forum, as well as a couple that have been asked on the question and answers. But if you are joining us today, feel free to keep asking us lots of questions, or you can certainly ask follow-up from questions that we answer as part of the discussion forum. And just before, so I don't forget, I just want to thank everyone for making these office hours really successful. We weren't sure if doing 5 would be too many, but we've had lots of awesome questions, so we hope you've enjoyed being able to interact with us a little bit more personally through this kind of MOOC environment. So without further ado, let's begin.
Okay, so we already have a question from Google Hangout. It's more of an administrative question, so we can just quickly answer this and then move on. So it just says, hi, just wanted to confirm, when are all the assessments due? For some reason, every now and then I cannot access key information on the edX website. Thanks, and thanks for the time spent teaching us.
All right, well, you're welcome. And we just looked up to make sure we had the date right. And the next week we will release the final module, which is just a lecture. It's just the one we recorded last week, kind of an updates lecture. And then along with that will be the final exam, final assessment, and an end of course survey that we hope everyone will fill out. And then you will have a little over a week and a half. So the course will formally end on August 14th, which is a Friday at 5 p.m. Eastern Daylight Time. And you will be able to watch videos and do all stuff. You know, you can watch all of the content of the course after the 14th, but the kind of assessment, and if you're getting a certificate and you want to be graded, all of that has to be done by August 14th.
Okay, so let's move on to the discussion forum. We have a lot of questions, and so we'll just see how many we can get through.
Sounds great.
So the first question, one person asked a lot of questions, so I'm just going to start and ask maybe the first 1 or 2, and then we can switch to somebody else to make sure everybody gets their questions answered.
That sounds great.
So the first question says, I've seen simulations of models of star formation where planetary bodies are flung out from the accretion disk into outer space. Of course, a free-floating planet would be very hard to detect, but is it possible that such a planet could come out of nowhere and pass through the solar system? And if that indeed happens, would it make a complete mess of the orbits of planets around the sun?
Cool question. Yeah, so we do think that there are these objects called free-floating detected from their forming disk. There's some evidence of maybe even seeing some of those in some star-forming regions, certainly in places like the Orion star-forming regions, where we saw some images when we talked about star and planet formation. There actually are a few objects that are at least planet mass objects that we've seen in star-forming areas. And so, but otherwise, if they've been around for a long time, they're very cool, so they're not giving off very much light, so they're difficult to detect. And if one were to pass near to our solar system, first of all, that would be very rare. I mean, between stars are so vast that even when 2 galaxies merge together, not a single star touches. Because the distances really are like we talked about in the first couple of modules of this class. But if one were to come close to our solar system, it could do a number of things. It could disrupt things like in the Kuiper belt, objects like Pluto or its various cousins, or the asteroids in the asteroid belt, and that could cause more comets and kind of raining down of kind of that extra material. it were really, really large and passed very, very close to a planet, it could disrupt maybe the planetary orbits, but it would have to come very, very close and be kind of, chances are it's also probably moving pretty quickly. And so it's the time that it actually would spend in the solar system would be very short. And so its ability to disrupt things might be very small. So it is theoretically possible that it's probably very unlikely. Much more likely for us to actually pass near a star or a large cloud of gas to like disrupt at least some of the things like the cometary material and things like that. That's actually a much more common scenario. And that probably does happen every few 100 million to billion years.
I think you just answered the next question, actually,
okay.
because it says, how close to the solar system should an alien star pass to have any effect on it? And do we have any observation or approximation of something like this happening in the distant future?
So I guess I did kind of answer it. Yeah, so it's actually a problem that I give students pretty frequently. I think I even wrote a comprehensive exam question here at Boston University about this a couple years ago. That, yeah, you can calculate just based on how many stars there are in the galaxy, what kind of the densities of stars are, and the motions of stars, how often that we will pass near another star. That's a fairly easy calculation to make. And it turns out that, and then you have to worry about how close it comes. But it turns out that, you know, for a star to come close enough to, you know, let's say hit the Earth, that essentially will never happen. I mean, statistically, that happens once every many trillions of years, I think. So, you know, has probably never happened. I mean, certainly hasn't happened to us, and likely will never happen. To get something that's close to, say, the Oort cloud, which is, if you remember from our planet walk, I think I talked about this very briefly at the end. It's this kind of cloud of cometary material that was kind of blown out of the early solar system, but still is on these very long orbits, you know, tens of thousands of years orbits. You can get past a star within the Oort cloud, which is about tens of thousands of AU from the sun, every about 100 to a few 100 million years. And that's something that likely does happen over and over again. It's also about the time scale for us to orbit the Milky Way once. And so we actually pass, when we do that, we're not in a perfectly flat orbit, we're a little bit inclined, and so we actually pass through the disk, where we're also more likely to run into clouds of gas or other stars. So certainly that can happen and probably does happen. But again, every few 100 million years or so. So we don't know exactly when the next one will happen, but it will.
Cool. So I'm going to move on to a question by someone else. This is from Atoli, and it says, a challenge question asked why Earth has a higher density than Mercury when Venus show the same higher density as Earth compared to Mercury, and for similar reasons.
So that's a great question. We talked about the densities of worlds being roughly more dense as you get closer to a star, and that's this condensation sequence. So it's easier to condense materials, denser materials, at higher temperatures. And so things like iron condense hotter than rock, condense higher than water, and things like that. And so if you look at terrestrial worlds, roughly, you see that the densest ones are closest to the star. But if you look at the Earth's density compared to, say, Mercury's density, Earth's looks much larger than it should be. And that's actually because of something that we didn't talk a lot about in class, I don't think we talked about at all, called compressed density. That you're putting all the rock and iron, which each has its own densities, but in a world that's, you know, pretty big like the Earth, gravity actually compresses it down and actually makes it smaller than it would be if you just had all of those chunks of iron and rock sitting out in space. So the gravity of Earth has actually compressed it down. The same thing is actually true of Venus. Venus is actually more dense than it should be for what it's made of for exactly the same reasons. Venus is, I think the question said it was our sister world. It's very close to the same mass and size, but it's not exactly the same. It actually is not quite as massive as the Earth, and so actually has a little less gravity kind of pushing it down. But actually, in the end, Venus is made of almost exactly the same material. So although it's a little closer than the Sun, has almost exactly the same, what we'd say, uncompressed density as the Earth. And that's just because of where we are in the solar system. The same materials could condense out of at that given temperature. So if we are at a place, both Venus and Earth are at a place where both rock and iron can pretty easily condense, but actually not anything else. No ices can condense. So kind of made of exactly the same material. Earth has more gravity and so is able to compress down the size of Earth a little more. So the measured density is a little higher than, say, Venus is. So Venus does also have a higher density than what we would expect from what it's made. So its compressed density is quite large, just not as large as the Earth's, just because it doesn't have as much gravity. But the same principle applies. The only real exception in there is that Earth and Venus really have about the same uncompressed density. They're made of the same material, and that's just because we were formed fairly close to the same place in the solar system.
Cool. Okay, so the next question from the discussion forum, there's two that are kind of similar, so
okay, cool.
We can just do those together. Gas planets appear to have migrated quite commonly based on Kepler data.
Mm-hmm.
What is the rate of migration? Is it slow enough to bring icy moons into a habitable zone long enough for life to evolve? And the second question asks about terrestrial planet migration.
Okay, well, let's do the gas giant one first. So in order for migration to happen, like at least what we think is one of the more common types of migration, it's an interaction with the gas disk. It's actually an exchange of momentum from the gas in the disk. And as the planet is accreting that material, is pulling that material on, it actually is exchanging momentum with the orbiting gas material. And that actually that can actually change the orbit of the planet itself. And so once the gas goes away, you don't have migration anymore. So that's actually what halts migration, is getting rid of the disk. And that, we think, at least for a star like our Sun, happens probably 10 million years, maybe in some cases up to 100, but probably not even that long, 100 million years. Probably about 10 million years is about as long as that happens. So it's a very short, in astronomical timescales, very short time scale. So you certainly can get giant planets migrating in. They can actually also migrate out. We of course talked about it mostly in the context of hot Jupiters, which must have migrated in. But there is evidence in our own solar system, we think, that Jupiter migrated in and then actually migrated out during the formation of the solar system. So as these planets are forming, they're also forming their moons. So you would bring in moons from the outer part of the solar system to be forming around these hot Jupiters or these worlds, and you would bring them kind of into habitable zones. But again, the time scales that we're talking, at least for migration to happen, are very, very short. I mean, so they're not the time scale of even terrestrial planet formation takes a much longer time, and certainly life to be set up takes a much longer time. However, your question is very good in that, if you actually have a Jupiter-sized planet that's formed in the outer solar system, and let's say it migrated into the habitable zone, although that planet as a big ball of gas probably isn't a place that you could set up life. Any moons that it would have that would be terrestrial and large enough to have water would actually have the ability to have water on the surface. So you could have habitable moons orbiting a giant gas planet, and that would be a scenario you have. And there's been science fiction books and whatnot written about those kind of scenarios. So that certainly could happen.
So the next question, also about planetary migration, asks, do terrestrial planets migrate? If they do, what does this say about the presumed stability of habitability of these worlds?
Oh, yeah, so terrestrial planets likely migrate as well. Again, most of that, all of that really happens in the first, 10 million years of the solar system's life, while you still have gas occurring, a gas disk happening in the system. So, once the gas leaves, if you have stable orbits, or relatively stable orbits, you will stay there for the rest of the time. It's not like Jupiter now is going to migrate in, or Earth is going to migrate right now in our own solar system. A lot of that likely happened during the formation of our solar system. But again, once the gas left, which was about 10 million years, all of that migration halts. So once that happens, if you have gravitationally stable orbits, they stay stable. They no longer are going to be doing these migration scenarios.
Awesome. So I'm going to move back to the Google Hangout.
Sure.
We have a question there.
Great.
From Dick Moser. What other crowdsourcing avenues are available, such as SETI at home, for internet-connected computers to help sifting data?
Oh, wow. I don't. Maybe Aurora knows more than me. I don't know of very many that where you just hook up your computer and use it for resources, but there very well may be. But certainly there's ones that you can be active. There's citizen science. I mean, it's kind of crowdsourcing, but through what we call citizen science. Things like Planet Hunters, which I think we talked about a little bit, which is a place where you can individually sift through Kepler data to look for new transits and actually discover planets, and people have done that. And there's a whole wealth of citizen science projects. If you go to galaxyzoo.com, I think it's .com, but if you just Google Galaxy Zoo, you'll find it. And there are all sorts of projects, from one called Galaxy Zoo, where you're actually looking at galaxies, but there are other astronomy ones, there are other biology ones. I've signed up to their email list. I'm always getting emails from them every time they have a new project. In fact, I even have an idea for one at some point when I have some free time to do a Galaxy Zoo project to actually look for binary stars. Yeah, you should check that out. But did you have another?
In the new SETI initiative that's going to get like $100 million of funding, they're definitely going to rely a lot on citizen science for citizens to look for signals. And they haven't fully figured out, I guess, how they're going to do it. But in their initiative, it says that they're going to rely on citizen science. Cool.
Well, I hope you guys all heard that this new SETI project that was just announced last week, that there is going to be a huge citizen science component where people will be asked to take a part in actually looking for signals in data. There's amazing things, but I really encourage everyone to look at Galaxy Zoo, the Zooniverse it's called now. There's lots of different projects in a lot of different scientific fields that citizens can get involved and get really involved and be really actively involved in the scientific process. So I'm most familiar with both the Galaxy Zoo project and the Planet Hunters project. Both have been very successful and have had amazing results. So
I think I read in the new SETI project also that they're basically doing a prize for the person who can come up with like the best signal to send out to aliens. And if you come up with the one that people choose, you get a large amount of money.
Oh, cool. Awesome.
Something like that.
So it could be lucrative too.
Yeah.
Awesome. Cool.
Okay, so back to the discussion forum.
Yeah.
I'm going to skip to a question by Valley MD.
Yeah.
So this is about SETI and Dyson spheres and all that. It
Yeah.
says, a less well-known SETI method involves scanning for technosignatures, IRAS, infrared astronomical satellite data, with most recently a WISE, which is Wide Field Infrared Survey Explorer, data survey of 100,000 nearby galaxies had been negative for excess IR emissions suggestive of Dyson sphere analogs. If found, such technosignatures might suggest the presence of potential Type 2 or Type 3 civilizations. How would one go about discriminating between a Dyson sphere signature and a natural source? Do these findings, along with other study results, lead you to support any particular explanation of the Fermi paradox? Or do you believe that there is far too little data available to draw any conclusions? Do you have your own favorite explanation of the Fermi paradox?
Wow, so that's lots of questions. So
Yes.
I will try to unpack them all. So first of all, let me tell you a little bit about Dyson spheres and this new study that ValleyMD is referring to. So Dyson sphere is this notion, it's a kind of hypothetical notion that if you had really technological society and they had amazing engineering abilities, they might actually be able to build a sphere around their solar system that would then capture all of the energy from their star, all right? So that you would be essentially perfectly efficient. None of the starlight would escape. You could harness it, and you would basically have, you know, infinite energy then if you could actually do that. You'd have to have the technological skills to build such a sphere. But imagine you could do that. You could harness all of the stars or sun's energy. So there was recently a project that was actually run by a good friend of mine, Jason Wright, who's a professor at Penn State University. And they actually looked through big, large data sets to see if they could look for signatures of this infrared light. And what they were looking for is things that didn't look like normal astronomical objects, because how you would maybe differentiate these things is if you really had built a sphere around an object, what you would expect is that it would be warm due to, like, you know, all the impending light hitting the surface or the inside surface, and it would kind of warm up whatever material it was made of, and then it would re-radiate at probably infrared wavelengths because it would be kind of warm. And so you would look for objects that were kind of glowing in the infrared in a very characteristic way of having you know, one specific temperature, but they wouldn't have any features that we see like on a star. They wouldn't have, you know, spectral features that you would see like on a star or a galaxy or things like that. And so they actually looked for these kind of signatures, and they found nothing. Now, at this stage, the data that they were using, although covered the whole sky, probably wasn't sensitive to probe very distant, you know, in the galaxy. Mostly what they're looking for is things within our own galaxy, and probably didn't have the data to do that. But it did show that there's probably no Dyson spheres nearby us in the galaxy. So no super technological civilizations have built them, at least that we can tell. You know, that there are a lot of other possibilities. You could imagine building a Dyson ring or a Dyson grid where you do let some say like starlight through, and that would be much more challenging to detect, because there you might actually see still the star at the center, but then you'd also see this kind of excess infrared emission from kind of the glowing metal or whatever they're using to like do it. And that is much harder to differentiate from a real astronomical source. In fact, I have a graduate student who has found such a class of objects that are kind of older stars where we actually can see the star, but we also see that it has an excess amount of, has way more infrared emission than it should. Now, we think that there's an astronomical way of explaining this, that we're actually probably seeing collisions of terrestrial bodies that are producing dust. That dust is re-radiating the infrared light. But one thing that we did briefly talk about was that these could be, you know, these Dyson rings or Dyson grids or something where you don't make a complete sphere, so you don't shield all the light from the star, but you shield some of it. So, but very hard to differentiate between those two things. The other thing that was asked was about the Fermi paradox, which is this kind of paradox, or this notion that basically, if I remember correctly, that we haven't seen aliens, or we haven't seen, you know, intelligent life And given the number of stars and the times, the time that the universe has been around, or our galaxy has been around, that like there should be enough time for someone to have like come and contacted us. I guess my thoughts are, when I look out at the universe and the galaxy in particular, and I see the, now hundreds of billions of exoplanets that we know about, and I see the possibilities of things like life and maybe even intelligent life, it's still, the distances are still extremely vast, and the timescales for actually getting to like a technological society are pretty long, right? So it took us even 4.5 billion years to get from forming a planet to actually being at least technological enough to send spacecraft into space, to have radio detections. I mean, which we've really only had now for ability to really sense radio detections from space for maybe a century, or maybe a little less than a century, to really have like the technology be strong enough to even get a signal or send a signal out from space. Really strong signals, probably not until the 30s. And so, we really as a society are really in our infancy. And so it's not clear to me that like the Fermi paradox means that we don't, the fact that we haven't seen anyone or seen a technological society means they're not out there. It just may mean that the timescales for like developing that kind of technology, as well as the distances, are just vast. They're really long. And so I don't actually think that rules out. It may mean that still it's rare. I'm certainly think that might be true, but I don't think it means they're not there. I also don't think, aliens built the pyramids and things like that.
So
I think, did I answer all the questions?
Yeah, Valiant, you had one more question.
Okay.
I didn't finish reading.
Okay.
There's a lot of questions. Anyways, it says, Stephen Hawking has expressed the opinion that trying to make contact with alien races could be risky. He has stated, if aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans. Do you agree with him on this matter?
I don't agree with him. So yeah, it's funny. There kind of are a couple different camps. There are people who really do think that if we were to contact, an intelligent alien species, that they would come and they would conquer us, and they would, come and they would enslave us or kill us or use up all our resources or whatever. And certainly that is a possibility, and certainly in our own human history, we have many examples of doing just that. But I also, I guess, maybe am an optimist, and I think that any really technological society, especially one that has figured out how to travel between or among the stars, is going to have a very different kind of social view. That doesn't mean they wouldn't accidentally bring disease, or there wouldn't be other social and challenges associated with contacting an alien species. But I guess I'm optimistic that any really advanced civilization will have advanced beyond, enslaving other intelligent species, and will be a much more benevolent. But people like Stephen Hawking are exactly right. It certainly is a risk. When we send signals out, which we have in the past, we're essentially saying, hey, here we are, here's where you find us. And if someone is not, benevolent, some civilization who really does want to come just use up all our resources, they're going to know exactly where we are. I don't think we have much to worry about that, but it is a concern that people do think about.
Cool. So I'm going to go back to the first question asker and continue on their list.
Sure.
This third question says, our galaxy is part of a supercluster called Laniakea, which is moving towards a point called the Great Attractor. Could you speculate what that is, and what would happen in a few billion years when more and more material is going to get closer to it?
Yeah. So basically, we're part of just to give you some geography of our place in the universe. Where we live in the Milky Way galaxy, which is part of a local group of galaxies, which really is a bunch of really tiny galaxies, but one other big one, the Andromeda galaxy, that we actually are moving toward very slowly, or at least it'll take a long time before we interact or merge with it. But we are also part of a larger supercluster of galaxies. And if you look into space, and we didn't talk about this much in our class because we were concerned with really stars and things in our own galaxy in this class. But if you look at how galaxies are distributed in the universe, it's like a web. They're kind of clustered along filaments, and that actually has to do with, we think, how the universe formed, and really from probably even when the universe was a fraction of a second old, that kind of initial pattern and that structure was initiated. And in fact, the structure itself tells us something about the beginnings of the universe in a very cool way. So if you look out, you actually see that galaxies and clusters of galaxies are clustered. And there's one part that's fairly near to us that's called the Great Attractor. And it's a very large, dense place of where many, many galaxies and clusters of galaxies are more clustered together. Aurora and I were talking about this just before the office hours began. I actually think that we are not necessarily moving that far towards the Great Attractor, but to be honest, I haven't done the calculation. You have to remember that the universe is expanding. And we're at a point in the universe expansion where it's actually accelerating. And so as the universe is accelerating, the points between two pieces of space are actually getting bigger. That's what's happening, that the actual space is expanding. And the only way we can move towards something is if the gravity is greater than that kind of space expansion. And for most places in the universe, gravity loses. One place where it wins is actually in our own local group. So Andromeda and us will actually interact and merge eventually. But once you get beyond, a few million light years, which sounds like a long distance, but it's really not in the grand scheme of the universe, you get into a point where the expansion of the universe overwhelms even gravity. And that's actually true, I'm pretty sure, for us and, say, the Great Attractor. It's not true for galaxies near the Great Attractor. So one of the things that you have to actually worry about when you're studying other galaxies and you're using their motions to try to understand, say, how far away they are or things like that, is you have to worry about, are they being pulled gravitationally towards something like another cluster of galaxies? And you definitely have to worry about that with the Great Attractor. But I believe the distance between us and, say, the Great Attractor is so great that the expansion and even acceleration of the universe will greatly overcome the gravity. But that's cool.
All right. So the next question by the same person asks, how big could a black hole be? If you have a neutron star that is fed with additional material from a close star, it eventually collapses into a black hole when it reaches the Chandrasekhar limit. What happens if you have a black hole that is being fed with more and more material? Shouldn't there be a limit similar to the Chandrasekhar one, which would cause something to happen once it's reached? Or is it that a black hole could just become infinitely large if there's enough material that you can feed into it?
Yep, theoretically. Well, I'm gonna be very cautious with some words here when we talk about the size of a black hole. So remember, a black hole, which again we didn't talk about much in this class, but a black hole is a point source. It's called a singularity. So in terms of its size, a black hole has no size. It is an object that has mass, but no physical size. So it has infinite density. And literally, if you remember when we talked about gravity in this class, we talked about gravity being the bending of space. We had the sheet that we were in the gym and we threw a ball around in the sheet and we could actually see the orbits, and that was cool. And if you had a black hole, you'd actually take the ends of the sheets and you'd actually kind of bend it in on itself. The gravity would be so great that bowling ball would sink just infinitely down into the floor, and it would pull the ends of the sheets in together so that space itself kind of would collapse in on itself. And that's what a black hole is. It's actually collapsed the fabric of space in on itself so that, in fact, there is no space. A black hole is occupying no volume, but it has mass. I know that sounds crazy, but it has mass but no volume. But a black hole can then continue to accrete material, can suck material in. And again, it's not getting any bigger, but it is getting more massive. And there is no theoretical limit that we know of for that. And in fact, we see black holes that are roughly the mass of the sun, or a few times larger. We see lots of those in our own galaxy. But even at the center of our galaxy is a black hole that is about 4 million times as massive as our sun. And so that's one that's a lot larger. And to be honest, we don't know exactly how you build one that big. It may be that you start with smaller or kind of intermediate sized ones and they accrete more material and become big ones. But we now know of black holes at the centers of some galaxies that are literally billions or 1 billion times as massive as our sun. So we don't know of any limit. If there's still material to suck into the black hole, it will continue to do that. Now, usually what happens is the black hole can suck things that are really, really close to it, but that's it. It's not like a black hole is much more powerful than something else of its mass. If you have if the sun turned into a black hole, right, nothing would really happen, right? The planets would keep orbiting because all they do is see one solar mass object. So the orbits would stay the same. Nothing would get sucked in. The sun all of a sudden wouldn't have more gravity. It would still have exactly the same mass. So black holes can suck material in, but it has to be really close to the actual point source. In fact, there is a physical part around the black hole called the event horizon, or the Chandrasekhar radius. That is what? I'm sorry, the Schwarzschild radius. Aurora corrected me. Thank you. Schwarzschild radius, or the event horizon, and that's basically a point of no return. It's not physical, but it's a point of basically it's the point where you could be moving even at the speed of light, and you could not escape the gravity of the black hole. And so that actually gets larger as you get more massive. But even for something the mass of the sun, that's pretty small. It's pretty small. So you have to be very close to get sucked in. Thanks for the correction.
No problem. So another question, I'm gonna skip down to a new person, trying to get every question answered.
Awesome.
It says, if any planet in a star system becomes an abode for life, even temporarily, it might spawn off rocks to carry bacterial spores. Could this mechanism be a source of life to get quickly restarted on worlds migrating into or through a habitable zone? If so, will we expect many worlds outside a habitable zone to carry evidence of past life due to their migration?
Oh, again, the migration process happens pretty quickly. So certainly, you could imagine there being some, I guess, interchange of materials if you had early bacteria or life or things like that. You've got lots of things happening. You've got migration happening. You probably have bombardment of a lot of the extra material that is forming, and you probably have material shooting off the surface of worlds as there's large impacts. And so you can imagine some exchange happening. But remember, all of this happens really quickly. Migration is happening while there's still gas in the disk. And so it's happening again in the first maybe 10 million years, as long as maybe 100 million years. At least what we know of the history of life on the Earth probably wasn't very much life happening that early in the Earth's system. Really until about 1 billion years did kind of life take to get a foothold on the Earth. And so it's probably unlikely that that the migration scenario is one that it helps exchange early life. Certainly, you could imagine if life is developing on a world a little farther away or a little closer, and you can actually transfer things via asteroid impacts or things like that. But again, the migration probably is not a major way that happens, just because it happens so quickly, and then as soon as the gas is gone, migration halts. You still get, again, asteroid impacts and other things like that. I mean, one of the things I like to think about is, probably one of the places where the earliest Earth fossils are is on the moon, because, Earth was being impacted by lots of things when the first life was developing on the Earth. And some of that material likely blew off the surface of the Earth and hit the moon, which is the closest body to us. And the Earth has, weather and plate tectonics and all this stuff that like erases our rock. It actually destroys our rock, destroys fossils. But the moon is actually pretty well preserved. So that's probably the place in the solar system that has the best preserved early Earth fossils, which is kind of cool to think about. Another maybe reason to go back and explore the moon more. Did I answer that?
Yeah.
All right.
So next question from Ejoli. One of the drivers for funding astronomy is the possible detection of biosignatures. This will further drive funding to try to determine what that life is, ultimately funding huge telescopes, possibly at the gravitational focus point, and interstellar probes. If it looks like the universe is lifeless, do you worry that astronomy funding may be decreased in the wake of the disappointment? Or will the focus of funding shift to other astronomical areas of interest?
Oh, that's a good question. Well, I think it'll take a while for us to figure out if indeed, like, we are living in a lifeless universe or galaxy, or if life is common. Actually, I think if life is common, we'll know in the next 10 to 20 years. If it's lifeless, it'll probably take us a little longer to reach that conclusion. How will that affect funding? Well, there is a lot of funding that's been put towards finding, other worlds that are like ours, and exploring with the idea of seeing if life is out there. But, astronomy is a field that's been around for hundreds of years, has been funded by governments and wealthy individuals during that time, well before we had any hope of answering questions about life elsewhere in the universe. So I guess I'm, again, optimistic that we will have many other exciting questions in astronomy that help us just understand our place in the universe and some of the amazing physical phenomena that are happening in our own galaxy, in our own solar system, and in our universe. And I still think there will be many funding streams. Some of the specific ones might dry up if we, at some point, really conclude that there's no other life or things like that. But I'm going to also say that I'm optimistic that we probably will find other life. But that's more of a belief than it is a scientific piece of evidence. Although, again, I think that we would be arrogant as a species to think that we're the only one. And every time we have thought that humans or Earth was somehow special, we found out we were wrong. So I think that history is on our side.
Okay, so back to some questions by...
I also noticed there's a couple in YouTube.
Oh, okay.
That I've gotten emails about. I don't know if you see those as well.
I can check now.
Okay.
I haven't looked into it.
All right.
Let me ask this next question from the discussion forum, and then I'll go to you.
Sweet.
Can we assume that the universe is expanding in a sphere-like fashion? If that is so, can we estimate where we approximately are in this sphere, close to the center or off towards one of the edges?
Tough question to answer. So the real answer, which you're not going to like, is that we are at the center of our own observable universe. And that's because, what we can see is limited by the light that is traveling to us. And so, although we do, the evidence is that anywhere we look, the universe is expanding uniformly. It's at least expanding at the same rate, at least at a given distance, no matter where you look, in which direction. So your first question is the answer is yes. Like it looks like it's expanding uniformly, and that the direction you look doesn't seem to matter. But the harder part of your question is that remember that the farther we go away, the farther back in time we are looking. And so you get to a point anywhere you look where you get to the beginning of the universe. You know, you get to where you're looking 14 billion years back in the past, and that's going to happen perfectly symmetrically around us to place us exactly in the center of our observable universe. Now, I know that's not very satisfying because you say like, well, where do we fit in the bigger universe? The answer is we don't know because we are limited by what we can see. Remember, the universe is all that there is. And so if you play that movie backwards, no matter where we were in the universe, we would end up back at us. Right? You could play that, you know, you could put a dot anywhere in a sphere, and if you collapse the sphere, you end up back at the dot. I know that's not very satisfying either. In reality, we could live in an infinite universe. I mean, it could be that the universe literally is infinite. It could be that it has some finite size. It could be that we live in multiple universes. At this point, we do not have the data or the evidence to make that claim. All we can say is that we can look out, and we can look out back we can see the very beginnings of the universe as we peer out farther and farther away, and that it looks exactly the same in whatever direction we look. The universe looks exactly the same, has the same patterns of galaxies, the same patterns of this thing called the cosmic microwave background, which is basically as far away as we can see. All of those things are exactly the same. And we literally are at the center of our own observable universe.
Cool. So I'm going to hop over to YouTube now.
Cool.
There's a question from Stephen Cohen. It says, maybe the rareness of finding, more of a comment, maybe the rareness of finding intelligent extraterrestrial life is because once it reaches a certain point of evolution, it destroys itself.
Ah, that's very true. So, I mean, one of the factors in the Drake equation that is part of, we discuss in this like module 9 that just launched yesterday, is this time scale of civilization. And a lot of that was put in there when the Drake equation was made in the 60s, was there because there was a worry that a technological civilization would inevitably blow itself up. And there was worry that we might do that in the 50s, 60s, and 70s, that we had become kind of a nuclear power, and that we had the ability to kind of annihilate ourselves. And so there was this worry that any civilization that gains the technology to become space-bound and have the ability to at least communicate with other worlds would also probably have the ability to build atomic weapons and may be able to annihilate itself. So that certainly is something that may happen some of the time in technological civilizations. We've seemed to have avoided it so far, which is good, but not all civilizations out there might.
So Stephen Cohen also posted another one that said, how important is it having an exoplanet solar system and not just one exoplanet around a star in order for there to be intelligent life? For example, doesn't Jupiter and the other larger planets act to deflect meteors/asteroids that would otherwise strike the Earth? But then again, the asteroid that killed off the dinosaurs apparently allowed for mammalian development.
Yeah. So there's actually some debate about whether or not you need a Jupiter-sized planet to have an acceptable habitable world. And my guess is the real answer is that you probably don't, but it's nice to have if you do. I mean, Jupiter certainly does act a little bit as a shield. It is something that has enough gravity to disrupt some of the material that would come raining down into the inner solar system. Jupiter either kind of sucks it up or deflects it out of the solar system. That is something that likely happens. It does once in a while actually take things and deflect them inward too. And those can be destructive, but as was mentioned in the question, those can be helpful. I mean, some of the mass extinctions, like the one at the KT boundary 65 million years ago that we think was at least partially responsible, if not totally responsible, for killing the dinosaurs, was hugely important for at least mammals. It killed off, you know, all of the large creatures on the Earth, and really led to the mammals kind of taking over, led to a lot more biodiversity. We think that some of those things actually are important as well. You know, it's also really important to probably have at least other material and have that material rain down on the planet in terms of having water on a planet like the Earth. Remember that the water on Earth probably didn't form here natively, that it probably formed in the outer part of the solar system and then was sent in probably on small planetesimal or, you know, small like moon-sized objects that kind of got incorporated in the Earth as it was forming. So Jupiter probably played a little bit of role in that too. So there's an ongoing debate of whether or not having things like a Jupiter is important or not. And my guess is, you know, we'll find worlds that are habitable that have Jupiters and some that don't.
Cool. So back to the discussion forum.
Yeah.
The next question is, what developing technologies look most promising to you regarding being able to resolve geographic features of exoplanets? What sort of resolution might be hoped for?
Oh, I mean, we're a pretty far ways off to actually be able to resolve structures on exoplanets. I mean, the best thing that can happen now is as exoplanets rotate and we can see brightness differences or orbit around their star, and we can actually get brightness differences, that maybe tells us about different features on their surface, or at least features in their atmosphere. And there's been some of that already done. We've been able to see that exoplanets have like hot spots or evidence of kind of weather in their atmosphere. We've not done that on any terrestrial ones yet. They've all been kind of big gas balls of gas exoplanets, you know, Jupiter kind of size exoplanets. But that will probably be the way that we get the first, at least, very low resolution glimpse of any kind of features will be through looking at small brightness variations. So when we probably this direct detection technique where we can actually image the actual exoplanets using things like a coronagraph or the star shade thing that I showed you, or that Professor Sarah Seeger talked about in her interview, and again, this latest module, Module 9, using a star shade like that and being able to really block out most of the light of the star will allow us to take images of terrestrial size exoplanets. But those images themselves still are only going to be point sources. I mean, again, these objects are so far away that they're just going to be points of light. But as those rotate and revolve around their stars, we'll be able to see slight differences in their colors and their brightnesses, and that will allow us to actually make very low resolution maps of their surfaces. And I think that's something that will happen in the next couple decades, but it's going to be a very, very long time before we have the technology to get any more detailed than that. I mean, we can barely do that with stars now, which are much, much larger than planets. So we have a long ways to go before we can actually take detailed images of a planet.
Cool. So since we have 7 minutes left, I don't think we're going to have time to get to everybody's questions.
Okay. Wow, lots of questions today. That's awesome.
If we don't get to them, we'll make sure to answer them in the discussion forum.
Love that idea. So yeah. Okay. So sorry if we don't get to your questions, but we will answer them in the discussion forum.
We've gotten to one question from every contributor. Just every contributor had more than one question.
Okay.
So
sounds great. Well, thank you for all your questions, those who contributed.
So to end, I thought this would be a really good question to end on. So like a 2-part question.
Okay.
Could you recommend more resources that could follow up and feed our curiosity even when this course unfortunately is finished?
Well,
And then there's another one that says, and lastly, what are the next steps for hobbyists that would like to continue learning in this field but do not plan to get a PhD? I'm personally making a living as a computer scientist and don't plan to change that. However, I got really interested in this area and would love to work even for free on the weekends and contribute as much as I can to astronomy-related projects if given the opportunity. Could you recommend something for enthusiasts like myself?
Yeah, well, okay, I have a couple ideas just off the bat. That's really awesome. I mean, there's a number of ways that people can be involved in astronomy. Certainly learning about astronomy, there's some amazing just web resources from, there's some other MOOCs out there that people are creating, so you can learn a little bit more about astronomy in kind of a similar format. There are amazing web resources, things like skyandtelescope.com and space.com, where you can just read up on some of the news that is literally, as you've seen, changing on a daily basis. There are most communities in the, at least United States and in some other parts of the world, have astronomical societies, and who meet at least once a month and chat about astronomy. Often get talks who come in, talks from people who are working in the field. So I sometimes go and give talks to local astronomical societies. So what I would do is look and see if your area has one. That would be a great place to be involved. Certainly getting involved in some of these citizen science projects where you can actually work on some of the science, and there are chat forums and discussion groups where you can interact with the scientists involved as well as other people doing the citizen science projects. I think there's a lot of opportunity for doing that, and I think those are all great things. Certainly there are some awesome books. I don't know if we have some in our, on the wiki for this class.
I can add some.
But Aurora just said that she would add some books that would be a great place, some further reading if you want to learn a little bit more about either exoplanets or kind of astronomy in general. There are some nice popular level books that aren't necessarily, textbooks that are expensive and not always that great. But there are some other ones that are great. But I would continue to look for other courses like this. Like I said, get involved in things like astronomical societies. There are other things in places around, again, in the U.S. A lot of this is happening where there are science discussions at local cafes or pubs that people give. There's an organization that's popping up in lots of cities called Astronomy on Tap. So you can see if your community has one of those and attend those events. There's lots of things happening out there. So I don't know.
Awesome. Yeah. Really exciting.
Yeah, lots of cool things happening. So I hope that gives you some ideas of how to continue learning.
You want to answer one more question?
Yeah, we'll do one more. Yeah.
Okay. So there's one more question, and it asks, the Fermi question might indicate that SETI will remain a fruitless search, even if technological ETI exists. The Breakthrough Prize Foundation has just announced $100 million funding to SETI. What are your thoughts on SETI, and what should the search be focused on in likelihood of success?
Well, yeah. I mean, I think spending some amount of funds for SETI is a great idea. I think the likelihood of success is pretty low, to be totally honest. I think, again, the distance scales we're talking about, the time scales for actually having not only other civilizations, if life is out there, to both evolve to be technological, but do it at the same time that we are, right? Remember, we've only been technological for a very short amount of time, and to have another civilization that's close enough to communicate, having done that same evolution, undergone that same evolution and technological building on the same time scale, is likely very rare. However, if we were to ever discover evidence of extraterrestrial intelligence, it really would be profound. Obviously, it would completely change our perspective of who we are as humans, who we are as members of the galaxy and the universe. And spending something like $100 million, although that is a lot of money, is really not a lot of money in the grand scheme of what our governments and other people spend kind of on a daily basis on many other things. So I think that's actually a small amount of money to take, a very risky project. I don't imagine we're necessarily going to find anything, but if we do, it's a ginormously amazing investment. So I support some of that, certainly for true. And to be honest, a lot of these projects are going to be looking around nearby stars, and they're going to be using radio data. And some of those projects are going to yield results from kind of more traditional science, because they're going to be taking data at various wavelengths and looking for various things around objects that can be studied for other purposes. So I actually personally am working with a scientist at the SETI Institute, and he's actually looking around a sample of stars that I've helped catalog. And the idea is that he's going to look for SETI pattern signals around them, but if there is radio, he's using it in the radio wavelengths, but if there's radio detections around those stars, that will be interesting to me scientifically for my research on small stars. So it's actually a very synergistic relationship that's not just going to look for ETs, which obviously is cool if we find them, but we actually can learn something about the astrophysics of the stars themselves. And I think doing these kind of joint ventures actually gives us more bang for our buck. So that's my take on that. Guess I'm a little biased. Cool. So I think we have run out of time for office hours number 5. I'm sorry we didn't get to everyone's questions, but that's because you guys asked so many excellent ones. So I guess we will give you a couple more things in this class, but no more office hours, but you'll get probably at least one more video email. Certainly we will send out the new module next week, and then the final exam, and good luck on that. We ask everyone to please fill out the end of course survey that will go out next week as well. So until next time, or until I see you again, or you see at least me again, have fun and stay curious.